Picture this: a signal, faint, structured, intelligently shaped, seems to whisper from the darkest place in the universe. Not from a star, not from a galaxy, but from the edge of a black hole. That's impossible, right? In physics, a black hole is the ultimate no-return zone. Cross the event horizon, and nothing, not even light, can escape. It's the boundary that makes a black hole black. And yet, from the outside, we've started to see their edges, a glowing ring of matter, gravity bent into a halo, casting a perfect darkness in the center. It's not sci-fi anymore. It's a photograph, the Event Horizon Telescope's historic image of M87*, and later, our own Milky Way's Sagittarius A. The shadow we're seeing? It's essentially the silhouette of gravity itself. That ring is not the hole. It's superheated gas spiraling around it, light bent and boomeranged by spacetime. The actual border is the event horizon, a one-way membrane where the escape speed exceeds light. If information can't get out, then whatever falls in, stars, planets, probes, or people, should be erased from the universe's memory. That's the classical picture, but quantum mechanics refuses to forget. Stephen Hawking showed that black holes should slowly leak energy, Hawking radiation. As quantum fluctuations near the horizon let one particle escape while its partner falls in. If that radiation carries even a whisper of the story of what fell in, then information might not die. It might be scrambled, encrypted, smeared across the rim, waiting for a scientist with the right decoder. What if the secret scientists inside a black hole aren't people at all, but information itself, trapped and yet, in principle, retrievable? That idea could rewrite our understanding of reality. Tonight, we'll chase that idea carefully. We'll move from the hard edges of observation to the dizzying cliff of theory, from the first photographs of black hole shadows, to the physics of event horizons, to the information paradox and what it means for life, consciousness, and the ultimate archive of the universe. We'll use only what the data allows, and we'll mark clearly what's testable and what's speculation. Because if black holes don't delete information, then somewhere, at the edge of darkness, the universe might be keeping a backup. If you love deep, evidence-based journeys like this, please subscribe and tap like. That tiny action makes a huge difference to how far these explorations travel. Thank you for helping this channel grow. Before we talk about secret scientists and lost information, we need a clean map. What is a black hole, in the clearest language possible? And how do we know? Start with the simplest picture. Compress enough mass into a small enough space, and gravity curves space-time so sharply that all paths forward lead inward. Somewhere around that compact mass, there is a boundary, the event horizon, beyond which every possible future points to the center. If a flashlight crosses that boundary, its beam cannot climb back out. If a radio antenna transmits from just inside the edge, no signal returns. The event horizon isn't a physical surface you'd bump into, it's a geometric border in space-time. From far away, though, we can see what the border does to light originating just outside it. Matter falling toward a black hole heats up and glows. Gravity warps the paths of photons into arcs and loops. This is gravitational lensing, and it creates a striking visual effect, a bright ring of emission with a central darkness known as the shadow. In 2019, the Event Horizon Telescope, actually a planet-scale array of radio telescopes, synthesized a virtual dish the size of Earth and imaged the shadow of M87*, a supermassive black hole 6.5 billion times the mass of the Sunday. In 2022, the same collaboration unveiled the first image of Sagittarius A, our galaxy's central black hole, about 4 million solar masses. These aren't artists' concepts. They're reconstructed images from petabytes of interferometric data. Here's what those images tell us about the rulebook. At the edge, there is a horizon-scale structure we can measure. The size of the ring matches what general relativity predicts for a black hole with that mass. That's a remarkable reality check. The theory that Einstein wrote a century ago is holding up under cosmic stress. Spacetime bends light severely near the horizon. The far side of the accretion disk appears above and below the blackened center because photon paths wrap around the hole one or more times before escaping to us. What you're seeing is not a neat, flat disk. It's a smeared panorama of a disk, lensed by extreme gravity. NASA's visualizations capture this carnival mirror, warping beautifully, and they're based on the same equations we test with the magnetic fields matter. In 2024, the EHT team released polarized images of SGRA, revealing organized magnetic fields near the horizon, clues to how black holes feed, flare, and launch jets. The details are complicated, but the punchline is simple. The edge of a black hole isn't quiet. It's a dynamic, magnetized, relativistic storm. Let's make it visceral. NASA recently built a high-fidelity, ray-traced plunge into a supermassive black hole, a guided fall to the point of no return. In one version, the camera slingshots just outside the horizon and escapes. In the other, it crosses the boundary and never comes back. The simulation labels the features you'd see: the accretion disk whipping by, the growing shadow, and the way time stretches and colors shift as you approach light-speed geometry. It's a visualization of equations, not a fantasy ride. Now, what really happens at the horizon? From a safe distance, you never watch an object actually cross it. Light from the infalling object gets redshifted, dimmer and slower, asymptotically freezing at the edge. From the falling object's own point of view, though, the crossing is uneventful for a large enough black hole. The killer isn't the horizon, it's the gradient in gravity, the so-called tidal forces that can stretch objects into spaghetti. For stellar mass black holes, that stretching could become fatal well before the horizon. For supermassive ones, the gradient is gentle at the rim. You'd cross without feeling a bump, only to face a stronger squeeze, much deeper in. The moral: the horizon is a causal boundary, not a physical wall. So far, nothing about this map sounds like secret scientists inside. That's because, classically, there can't be any conversation from inside to out. The horizon severs causal contact. If you want a story about messages leaking from the dark, you need to bring in quantum rules. Enter Hawking's insight. Near the horizon, space-time's quantum fluctuations can be pictured as pairs of particles blinking into existence. One falls in, one escapes, and the black hole loses an infinitesimal bit of mass. Over unimaginable timescales, the whole can evaporate. If that outgoing radiation is perfectly thermal, pure noise, then information is lost. That would break quantum mechanics' core promise that information is conserved. If, on the other hand, the radiation subtly encodes a record of what fell in, then the universe's ledger balances and information survives. This standoff, the black hole information paradox, has animated decades of research. Here's where our title starts to make sense, metaphorically but meaningfully. Think of scientists inside a black hole as everything that could have been measured, the microstate of the matter that fell in, the patterns, the correlations, the story. If that story is preserved at or near the horizon and leaks out in Hawking radiation, then, in principle, the universe hasn't deleted the scientists. It has compressed their notebooks into the static. That doesn't mean we can decode them with today's telescopes, but it changes how we think about the cosmos. A universe that never forgets, even in the darkest places, is a universe where physics is, at its core, a perfect librarian. Of course, there are competing proposals, firewalls that torch anything at the edge, wormhole, like descriptions that teleport information through quantum entanglement, holographic dualities that rewrite a 3D interior on a 2D boundary, Each is a different way to reconcile gravity and quantum mechanics without breaking either. We'll visit them later, but keep the ground rules close. The event horizon is a one-way border. The shadow and ring are real, observed features, and the information paradox is a live, unsolved puzzle with profound consequences. One last clarification before we go deeper. When we ask, could this change life forever? We're not promising sci-fi shortcuts through space. What changes life is knowledge. If black holes don't delete information, then the fundamental operations of physics, the way quantum bits transform, entangle, and survive, are universal. The same mathematics that keeps a black hole honest also underpins secure communication, quantum computing, and error correction. The cosmos might be telling us, build your machines this way and you can compute at the edge of impossible. That's not a claim about rescuing astronauts from beyond the horizon. It's a claim about rescuing truth from the brink of oblivion. So we have the rule book, horizons that isolate, lensing that reveals, data that may or may not leak. In the next chapter, we'll stage a careful thought experiment, send a scientist toward the edge, track every photon, and ask what the universe allows us to learn without cheating. And along the way, we'll mark what is observation, what is theory, and what is still a daring guess. That's because, classically, there can't be any conversation from inside to out. The horizon severs causal contact. If you want a story about messages leaking from the dark, you need to bring in quantum rules. Enter Hawking's insight. Near the horizon, spacetime's quantum fluctuations can be pictured as pairs of particles blinking into existence. One falls in, one escapes, and the black hole loses an infinitesimal bit of mass. Over unimaginable timescales, the whole can evaporate. If that outgoing radiation is perfectly thermal, pure noise, then information is lost. That would break quantum mechanics' core promise that information is conserved. If, on the other hand, the radiation subtly encodes a record of what fell in, then the universe's ledger balances and information survives. This standoff, the black hole information paradox, has animated decades of research. Here's where our title starts to make sense, metaphorically but meaningfully. Think of scientists inside a black hole as everything that could have been measured, the microstate of the matter that fell in, the patterns, the correlations, the story. If that story is preserved at or near the horizon and leaks out in Hawking radiation, then, in principle, the universe hasn't deleted the scientists. It has compressed their notebooks into the static. That doesn't mean we can decode them with today's telescopes, but it changes how we think about the cosmos. A universe that never forgets, even in the darkest places, is a universe where physics is, at its core, a perfect librarian. Of course, there are competing proposals, firewalls that torch anything at the edge, wormhole, like descriptions that teleport information through quantum entanglement, holographic dualities that rewrite a 3D interior on a 2D boundary. Each is a different way to reconcile gravity and quantum mechanics without breaking either. We'll visit them later, but keep the ground rules close. The event horizon is a one-way border. The shadow and ring are real, observed features, and the information paradox is a live, unsolved puzzle with profound consequences. One last clarification before we go deeper. When we ask, could this change life forever? We're not promising sci-fi shortcuts through space. What changes life is knowledge. If black holes don't delete information, then the fundamental operations of physics, the way quantum bits transform, entangle, and survive, are universal. The same mathematics that keeps a black hole honest also underpins secure communication, quantum computing, and error correction. The cosmos might be telling us, build your machines this way and you can compute at the edge of impossible. That's not a claim about rescuing astronauts from beyond the horizon. It's a claim about rescuing truth from the brink of oblivion. So we have the rule book, horizons that isolate, lensing that reveals, data that may or may not leak. In the next chapter, we'll stage a careful thought experiment, send a scientist toward the edge, track every photon, and ask what the universe allows us to learn without cheating. And along the way, we'll mark what is observation, what is theory, and what is still a daring guess. Imagine we launch a small probe, call it Vesper, straight toward the Milky Way's central black hole, Sagittarius A. Inside, an atomic clock, a strobe beacon, and a wide-angle camera. On Earth, we keep a perfectly synchronized twin clock and a dish network listening to every tick and flash. The experiment is simple. Compare Vesper's time to ours as gravity grows, and map what light can still escape as the probe descends. 2 clocks, 1 horizon. First, the map we trust. A black hole has a one-way boundary called the event horizon. Cross it, and every path forward, literally every future, points inward. There's no bouncing a signal back out. From far away, though, we can see what happens just outside. Matter heats and glows in an accretion disk, while gravity bends photon paths into a warped, halo-like shadow and ring. The very structure the Event Horizon Telescope revealed at M87 in 2019 and at Sagittarius A in 2022. These images aren't concept art. They are reconstructions from now, press record. As Vesper dives, 2 things dominate the story we receive: gravitational redshift and time dilation. Each flash from the probe's strobe arrives a little redder and later than the last. The closer to the horizon, the more extreme the shift, until the outbound light is stretched beyond detection. To our distant clocks, Vesper appears to slow, then stall, then fade, never quite crossing the edge. From Vesper's own point of view, though, the clock ticks normally, and the horizon is crossed in a perfectly ordinary finite time for a supermassive black hole. This is the cleanest example of 2 truths in general relativity. What you see depends on where you are. Our radio link tells the same tale. We ping the probe. The return takes slightly longer than a straight-line light, time would predict, a classic gravity signature known as a time delay. Near massive bodies, spacetime itself adds a bit of travel time. One of relativity's original tests. Stack up enough gravity, and every round trip stretches. Near a horizon, the outbound signal's frequency is pummeled downward until there's effectively no recoverable message left for us to decode. The camera feed is weirder. As Vesper approaches the black hole, the view of the surrounding disk becomes a funhouse. Gravity bends light so severely that the far side of the disk appears above and below the dark center. You're not seeing a neat, flat platter. You're seeing a panorama wrapped by spacetime. NASA's visualizations show this carnival mirror effect vividly. They're built by ray tracing the very equations that the EHT tests against real data. Something else pops. A brightness asymmetry in the ring. The side where the gas orbits toward us looks hotter and brighter. The opposite side dims. That's relativistic, Doppler, beaming, the headlight effect of near light speed motion. It's been emphasized in both NASA's black hole simulations and EHT analyses as a key clue to geometry and spin. In short, motion sculpts what we see. Dive deeper and the geometry tightens. There's a special radius, the photon sphere, where light itself can loop the hole in an unstable orbit. For a non-spinning Schwarzschild black hole, it sits at 1.5 times the Schwarzschild radius. Photons that skim here can orbit once or several times before peeling away to our telescopes, creating the possibility of delicate, lensed rings within the ring in ultra-sharp images. It's a theoretical landmark in every strong gravity visualization. Another critical radius marks the inner edge of stable traffic for matter, the innermost stable circular orbit, ISCO. For a non-spinning black hole, it lies at 3 times the Schwarzschild radius. Inside, circular orbits fall apart and the plunge accelerates. Spin drags the ISCO inward, which is why measuring variability and spectra near this edge can reveal a black hole's rotation. Think of the ISCO as the last roundabout before the cliff. What about the infamous spaghettification? Tidal forces, the difference in gravity between head and feet, do the stretching. For stellar mass black holes, the gradient near the horizon can be fierce. For supermassive ones like Sagittarius A, the crossing itself could be uneventful, with the fatal squeeze coming much later. Deep inside, NASA's 2024 supercomputer fly-through lays out both scenarios, one trajectory that skims and escapes, another that crosses the line and never returns. Back to our two clocks. Could Vesper encode a final message that we might fully recover? Suppose we program the strobe to blink prime numbers faster and faster as it falls. From our vantage point, each bit is redshifted and delayed more than the last. We do receive a long series of clean, early pulses, but the ending stretches into a whisper and then silence. In practice, there's no way to extract the complete string from outside. The last pieces are pushed into impossibly long wavelengths and lost in background noise. This is not about the transmitter failing, it's about the rules. The horizon enforces a causal silence, yet silence is not the same as erasure. Here we reach the paradox flagged in Chapter 1. If black holes eventually emit Hawking radiation, and if that radiation carries subtle correlations, then the story of everything that fell in might be preserved, shredded, and spread out over inconceivable times, but not destroyed. In that view, the scientists inside are a metaphor for information, what was measured, written, remembered in the quantum state of infalling matter. Whether and how that story leaks out is the central riddle, the information paradox that modern theory attacks with tools like quantum entanglement, holography, and error correction. We'll go there soon. For now, the experimental picture stands. Outside observers watch the fade and freeze. Inside observers feel nothing special at the rim. Both are true in their frames. A final twist for our video editors. The ring and shadow you'll cut into the hook aren't the hole itself. The shadow is a lensed silhouette, roughly twice the size of the actual event horizon, carved by photon trajectories that never reach us. That's why the EHT's donut is so valuable. It measures space-time curvature directly, not a painted surface. And when EHT teams map polarized light at Sagittarius A, they're tracing magnetic fields right at the brink, evidence that the edge is a relativistic, magnetized storm rather than a quiet void. Those magnetic threads likely help funnel and fling energy into the larger environment, linking black hole edges to galaxy-scale feedback. So, what have our two clocks taught us? From far away, time slows, light reddens, images warp. The horizon is a perfect sensor. From up close, the crossing can be ordinary for giants, but the descent becomes inescapable. The inner geometry and fields roar. For the script, every beat near the edge is a tension between what the universe shows and what it hides. A built-in narrative engine you can hear in the audio, even when the visuals are simple. In the next chapter, we'll take this tension and turn it into a clean thought experiment about information. We'll send a second probe with an entangled partner at home and ask what quantum theory allows us to infer without cheating. Causality. The rules won't budge, but our understanding might. Let's upgrade the experiment. Our first probe, Vesper, dives towards Sagittarius A. This time, it carries a tiny vault of entangled qubits, paired with twins we keep safely on Earth. Call the ground array Keeper. Before launch, each pair is locked into a quantum relationship so tight that measuring one instantly fixes what the other will show when results are compared later. That's entanglement, not a radio, not a wire, but a correlation that stretches across distance. Now, here's the crucial rule you can hear in every word that follows. Entanglement can't send a message by itself. The outcome on Vesper looks random. The outcome on Keeper looks random. They line up only after we compare notes with a classical signal, an ordinary, light-speed conversation. No classical link, no usable message. This no-signal promise is what saves causality, and it will keep saving it all the way down to the horizon, the setup. We synchronize clocks. We agree on measurement bases. We run a quick Bell test while Vesper is still far out, just to confirm the correlations are alive. The statistics pop exactly as they should, stronger than any classical model can explain. We stop the pre-flight checks. Vesper burns forward. As gravity builds, Vesper keeps sampling its half of the pairs, sometimes along one axis, sometimes another. Keeper follows the agreed pattern on Earth. Immediately, two clocks begin to disagree about when things happen. Time dilation and redshift reappear, just as in Chapter 2. Vesper's data stream arrives increasingly delayed and smeared until the last bits stretch into silence. If it crosses the horizon, the classical channel dies for good. So can entanglement sneak a message out? No. Even if Vesper performs clever measurements right at the brink, Keeper's local outcomes remain indistinguishable from noise. Without a classical compare notes step, impossible once the horizon is crossed, there's nothing to decode. Entanglement gives you correlation, not control. It's a silent handshake, not a shout. That non-negotiable limit is our anchor. Keep it close as we push into deeper water. What happens to the correlations themselves when one partner falls in? Here our story meets the black hole information paradox head-on. If Vesper's qubits tumble past the event horizon, do their quantum stories die? Or are they somehow preserved, smeared across the edge, encrypted in the outgoing radiation, recoverable in principle? Theory offers two powerful signposts: the Page curve and the Hayden-Preskill insight. The Page curve, intuition version. Imagine a black hole formed from ordinary matter, stars, gas, whatever, and imagine it very slowly radiating away via Hawking radiation. If that radiation carries zero information, its entropy should just rise and rise. But quantum mechanics says information shouldn't be lost. The entropy of the radiation should eventually turn over and head back down as correlations leak out. That bend is the Page time, roughly when the hole has radiated about half its initial entropy. Past that point, the radiation is less random than it looks. Subtle patterns begin to matter. In plainer terms, a sufficiently old black hole behaves like a careful librarian, not a shredder. Hayden-Preskill, intuition version. Throw a fresh quantum diary, like Vesper's last qubit, into a very old, very chaotic black hole. If the hole scrambles information fast, as many models suggest, then, after a short scrambling time, the new info starts to seep back out in the Hawking glow. To recover it, an outside observer would need 1. The earlier radiation, and 2. The next trickle of new radiation. With a perfect decoder, the diary could be reconstructed surprisingly quickly. The catch is brutal. Building that decoder is astronomically hard. Think computational Everest, then add a few dozen Everests on top. Notice what both ideas preserve. No signal outruns light. There is no instant messaging from inside to out. The recovery is a story about correlations in the long, patient limit, not about a last-second text from beyond the horizon. And if the black hole is young, before Page time, recovery is even bleaker. The shredder mode dominates. All of this raises a famous tension called monogamy of entanglement. A single qubit can't be maximally entangled with two different partners at once. Near the horizon, we're tempted to assign overlapping entanglements between outgoing Hawking quanta, infalling partners, and the rest of the radiation. Try to satisfy all of them, and you can get a paradox. One proposed escape, the AMPS firewall, says the horizon isn't no drama after all. It's a wall of high-energy quanta that burns anything crossing, breaking one of the entanglements to rescue consistency. Another escape route is black hole complementarity and, deeper still, holography. Different observers get different but consistent descriptions of the same physics, and the interior might be redundantly encoded on the boundary in a way that avoids double-counting entanglement. Either way, the math is telling us that space-time and information are welded together more intimately than our everyday language admits. How do we narrate that without drowning the viewer? We pin the emotional beats to clear images. Visual beat 1, abstract lines linking twin specks. The entangled pairs, shimmering but mute, no arrows, no messages, just bonds that only light-speed comparison can reveal. Visual beat 2, a slow, tasteful dissolve from tidy links to a swirling fog around the black hole, scrambling as a visual metaphor. Patterns still there, now rearranged beyond easy recognition. Visual beat 3, a ledger motif appearing faintly over the horizon. The universe keeps accounts, then fading, because the decoder is beyond our means. For the voiceover, keep the rhythm clean. Entanglement is a promise about togetherness, not a permission slip to talk faster than light. If the horizon cuts the phone line, the promise persists as a pattern, not as a message. And patterns can, in principle, be reclaimed if you're patient enough and impossibly clever. Let's stress. Test the rules with a tempting trick. Quantum teleportation. In labs, teleportation lets us transfer an unknown quantum state from A to B using A, a shared entangled pair, and B, a few classical bits sent after a measurement. Teleportation feels like magic, but it's honest. The classical bits enforce light speed limits. Try it at a black hole's edge. Could Vesper teleport a state out to Keeper? Only if the classical side channel escapes. Once Vesper crosses the horizon, that channel dies. The protocol refuses to cheat. Teleportation remains loyal to causality. If entanglement won't carry messages and teleportation won't cross the border, what can we learn by launching quantum partners toward the edge? Two things that matter for our bigger thesis. We can separate drama from data. For a supermassive black hole, the crossing is physically calm for the infaller, but epistemically brutal for us outside. We don't get the last word. We get a long, red-shifting goodbye. The soundtrack here is a slow fade, not a scream. We can motivate the stakes. If nature conserves information even in the worst furnaces it built, then information is not just a bookkeeping trick, it's a physical resource that shapes spacetime. That idea already reshapes how physicists think about quantum error correction, holography, and the architecture of reality itself. Where does "it could change life forever" enter the picture? Not through fantasy rescues from inside the horizon, but through design principles we can steal from the cosmos. The universe appears to protect information with redundancy, scrambling, and clever encodings. That's exactly what our most ambitious technologies, fault-tolerant quantum computers, privacy-preserving networks, ultra-robust storage, will need to scale. The black hole is a terrifying object, but it might also be the ultimate syllabus for how to compute when failure is not an option. One last scene to close the chapter. Vesper's classical beacon has vanished into silence. Keeper still holds half the entangled pairs. In the control room, a wall of screens whispers random bits, pure noise, as advertised. And yet, somewhere in that noise, if the boldest theories are right, the universe is busy balancing the books, ensuring that what fell in is not erased but rephrased, encrypted into the fabric of reality. We may never have the decoder, but knowing the ledger exists changes the way we look at the night. In the next chapter, we'll leave the thought experiment for observations, flares from SGA, polarized light at the brink, and how real data fences in the wildest ideas about horizons, firewalls, and holography, so our script stays daring and honest. Before we sprint into wild theory, let's anchor ourselves to what we've truly seen, not animations, not metaphors, measurements. 3 pillars hold up the empirical side of our story. The ring and shadow images at event horizon scale, the magnetic fields threading that edge, and the flares, brief storms that light up the black hole's neighborhood and let us track matter on relativistic orbits. We'll keep each pillar honest: who saw it, when, and what it means. Pillar 1, the ring and the shadow. In 2019, the Event Horizon Telescope, EHT, a planet-sized array of radio telescopes, unveiled the first horizon-scale image of a black hole, M87. That donut is not the hole itself. Its emission from superheated gas lensed into a ring by extreme gravity, framing a central shadow whose size matches general relativity's predictions for a black hole of that mass. In 2022, the EHT repeated the feat for our own galaxy's central black hole, Sagittarius A. Different object, consistent physics, a ring whose diameter agrees with Einstein's math. These are reconstructions from petabytes of interferometric data, not concept art. Pillar 2, magnetic fields at the brink. Seeing a ring is one thing, feeling its texture is another. In March 2024, the EHT collaboration released the first polarized image of SCAR A. Polarization is a fingerprint of magnetic fields. Map it, and you trace how fields thread the gas, skimming the horizon. The result? Organized magnetism right at the edge, evidence that the boundary region is a magnetized, relativistic storm, capable of shaping how the black hole feeds and potentially how it launches energy back into its environment. This is the first time we've measured polarization this close to SCAR A. For your visual edit, that means our hook can honestly cut from the classic EHT ring to a polarized view with field lines. No speculation required. The science says the horizon's neighborhood isn't quiet, it's structured. Pillar 3, flares, and the hot spot dance. SCAR A doesn't blaze like a quasar. It flickers. In the near-infrared and X-ray, it produces short, sharp flares, bursts that can last tens of minutes to a couple of hours. With the gravity instrument on ESO's Very Large Telescope Interferometer, astronomers did something astonishing. During multiple bright NIR flares in 2018, they tracked the orbiting motion of the light source itself. The sky positions traced clockwise loops spanning 150 micro-arcseconds in a few tens of minutes, consistent with matter whipping around at roughly 30% of light speed near the innermost stable circular orbit, ISCO. In other words, we watched a compact hotspot go round the black hole in real time. Since then, teams have expanded and reanalyzed these events. Joint fits to astrometry, the tiny position changes, and polarimetry, how the light is polarized, strengthen the hotspot interpretation and probe the local magnetic geometry guiding the flares. Newer work continues to model these loops and their light curves with general relativistic ray tracing to test whether the orbits, periods, and polarization swings match what we expect near a Kerr black hole. The headline, more than a vibe, there's kinematics in the data. In X-rays, long monitoring campaigns with Chandra, XMM Newton, and NuSTAR show that SGRA flares with a range of amplitudes. Most are modest. Some are hundreds of times brighter than quiescence, and likely occur about once or twice per day on average, depending on sensitivity and time window. The rate appears to cluster and vary over years, which itself is a clue to the engine that powers them. For our script, you can truthfully say, the black hole dozes, then pulses, and we've been counting those pulses for decades. Why these 3 pillars matter to our story. Together, they fence in our imagination. The ring and shadow anchor the scale and geometry of spacetime at the edge. We're not guessing the size of the playing field. We measured it. The polarized view shows magnetic order in the chaos, supporting models where fields thread, twist, and channel energy at the brink. That's vital if we're going to talk about how information, or at least structure, survives and propagates near a horizon. The flares give us timers and tracers, orbits in tens of minutes at a few gravitational radii, polarization angles that rotate with the motion, spectra that hint at synchrotron processes and relativistic beaming. They convert "there's a storm" into "here's the storm's clock." From observation to narrative, how to cut this honestly opening beat. Start on the classic E ring of SGRA, then crossfade to the polarized version with field line overlays. A lower third can read 2024. Polarized image of SGRA reveals magnetic fields near the event horizon. This is not hype, it's the actual claim. Rhythm beat, audio. Every few hours, the galactic center twitches. Not loudly, bright for a heartbeat, then quiet again. As you say that, show a tasteful light curve motif or a subtle time lapse of the Milky Way's center. No cliches, just a pulse. Then cut to an artist's tactful line animation of a looping centroid to illustrate gravity's astrometry. Label it clearly as a visualization of data. Reality check, VO. We've literally watched something go around the black hole in tens of minutes at a third of light speed. A tiny caption can cite ESO, gravity, 2018. What we can and cannot say on the mic, we can say, the ring size supports a Kerr black hole consistent with general relativity. The magnetic fields near SGRA edge are mapped via polarization. Hotspot, like motion during flares, is observed and modeled with relativistic orbits. X-ray flares are real, frequent, and variable in rate and brightness. We should not say, we've imaged the photon ring subrings directly, or we can read messages from inside the horizon. The ultra-thin photon ring is a predicted, not yet isolated, feature that likely needs future, longer baselines, possibly space interferometry, to cleanly separate. Keep that for later chapters, as a frontier, not a done deal. Bridging back to the secret scientist's idea. If the horizon is where information goes to the brink, these observations tell us the terms of engagement. The edge is hot, dynamic, and magnetically organized. It scrambles patterns quickly, and it gives us clocks, orbital periods of hotspots, that match the scale where quantum gravity-flavored arguments begin to matter. Our title isn't claiming a radio chat from inside. It's pointing to a deeper truth. The universe might protect and process information even in its darkest computers. The data don't prove the grand claim, but they permit it and shape it. Every bold idea about black holes must face the same cold rule. If it can't, in principle, leave fingerprints on the sky, it isn't physics yet, it's poetry. So in this chapter, we pin three competing stories to the wall: firewalls, complementarity, and holography, and ask what each one dares us to measure. Start with a nightmare that saved the paradox from going in circles, and to the firewall. In the classic picture, an astronaut crossing the event horizon of a supermassive black hole feels nothing. No shock. No wall, just darkness and the long fall inward. But quantum bookkeeping has a jealous rule called the monogamy of entanglement. If outgoing Hawking quanta are entangled with earlier radiation to preserve information, they can't also be perfectly entangled with modes just inside the horizon. Something has to give. The firewall proposal says what gives is the astronaut. The horizon becomes a searing veil of high-energy quanta that annihilates no drama. It's brutal, but it cleans the math. How would a firewall leave evidence outside? Not directly. The horizon still censors, but a firewall rewrites the near-horizon vacuum. That could, in principle, perturb the statistics of radiation and the detailed structure of light near the edge. Minute changes in spectra, polarization, or the timing of the smallest flares. Think of it as a fingerprint on the glass. not the culprit in frame, but a smudge pattern that standard models struggle to make. Next, a gentler yet equally radical move, black hole complementarity. Here, two stories coexist without contradiction because no observer can compare them. To the astronaut falling in, the horizon is smooth, no fireworks. To a distant observer, everything that approaches the horizon is scrambled and re-emitted from a stretched, hot quasi-surface just outside it. The two descriptions disagree only about events that no single witness can check. Physics stays consistent by refusing an impossible comparison. Complementarity makes a falsifiable promise. What the far observer sees must obey ordinary quantum rules, including unitarity. That means the long record of emissions, the tremble of flares, the polarization swirls, the subtle statistics of light, should fit a story where information isn't erased but recoded near the edge. Testable? Yes, but not with a single photo. You need time series discipline, light curves, spectra, and polarization measured over years across bands with enough precision to catch the accounting at work. Finally, the idea that turned a guess into a framework: holography. In a holographic universe, the interior of a black hole, the whole 3D drama, can be redescribed as data living on a 2D boundary with an ordinary, non-gravitational quantum theory. In practice, we don't get to pick the easiest version of that duality for the messy, rotating black holes in our universe. But the principle has teeth. It says spacetime geometry is not fundamental. It emerges from patterns of entanglement. It says error-correcting codes, the same logic we use to protect qubits in a quantum computer, looks suspiciously like the logic nature uses to protect the inside of a black hole from small glitches outside. If that's true, then the black hole is not just a furnace. It's a device that processes information with ruthless efficiency. What would count as evidence for that? Not a lab demonstration of ADS, CFT for Sagittarius A. Instead, consistency checks when we model the near-horizon region with magnetized, turbulent plasma and ray trace the light. Does a code-like redundancy show up in the statistics of fluctuations? Do we see universal relations between variability timescales, polarization swings, and spectral slopes that look like error-correcting signatures, not just thermal noise? We can't invert the decoder, but we can look for the hallmarks of its design. To make this concrete, imagine 3 observational stress tests. Not tomorrow's miracle, but steps that move the dial. Test 1. The polarization clock. During bright, near-infrared flares, the polarization angle can rotate as a compact hotspot orbits near the innermost stable circular orbit. In standard models, that rotation tracks a tidy dance between orbital motion and magnetic geometry. In firewall-like models, the near-horizon vacuum is altered. The local field structure and the phase relation between flux and polarization might show systematic departures, drifts that don't match any smooth disk geometry, or phase lags that require an exotic emission layer. The challenge is discrimination. Can improved cadence and multiband coverage reveal a repeatable anomaly? If yes, no drama takes a hit. Test 2. The thin ring frontier. Gravitational lensing predicts an ultra-thin photon ring made of light that skims the hole and loops around once or multiple times before escaping. In ideal conditions, those subrings should carry a self-similar structure, echoes at geometric intervals, like a fractal signature of the geometry itself. They are desperately hard to isolate, but longer baselines, better calibration, and clever image domain statistics could start to bound how much power lives in those razor-thin features. Why does this matter for information? Because any deviation from the clean Kerr expectation, once astrophysical clutter is tamed, forces our hand about the near-horizon state. If the last, thinnest rings look too bright, too jittery, or mismatched in phase, We've learned that the edge carries extra structure. Test 3. The noise is the message. In a turbulent, magnetized flow, brightness flickers with red noise power. Lots of slow variations, fewer fast ones, following a slope. But scrambling near the edge could imprint universal microstructure, preferred timescales, tied to the geometry and the speed of information mixing. If, across many flares, we extract power spectra and find the same breaks and knees that scale precisely with the expected gravitational radii and spins, we stack evidence for a dynamical code at work. If instead we see stubborn mismatches, too much short timescale coherence where only noise should live, we confront models that treat the horizon as empty space. Either way, the statistics push the story. Now knit the three big ideas back into the human scale question. Why should any of this change life? Because every one of these tests circles the same principle. Information is physical. If black holes protect it with redundancy and fast scrambling, then the best designs we build, from quantum networks to planetary scale archives, will do the same. Spacetime becomes a teacher. It tells us to spread risk, to entangle cleverly, to let noise carry signal when direct paths are blocked. The practical translation is stark: secure communication that laughs at eavesdroppers, fault-tolerant computation that shrugs off local failure, storage that survives disasters because knowledge has more than one home. Be careful. This isn't a promise that we can mine a black hole for hard drives or pull messages from beyond the horizon. The promise is subtler and more powerful. If the universe refuses to delete information, even in its most violent machines, then we can engineer with that stubbornness as our blueprint. The math that keeps a black hole honest can keep our systems honest. That is how an idea at the edge of a galaxy changes life in a living room. One more image to hold while the visuals stay simple. Picture the ring, bright on one side where matter whips toward us, dim on the far side where it flees. Now imagine a transparent overlay, lines curling like iron filings, the magnetic field traced by polarized light. Inside the darkness, there is no picture we can show. But just outside, the universe is writing in a script of light, timing, angle, intensity, noise. Learn to read that script, and you read the rules that decide whether truth is lost or saved at the brink. So the scorecard, for now, firewalls demand drama at the rim and dare us to find its echo. Complementarity lets two consistent stories coexist and challenges us to audit the books from the outside. Holography whispers that spacetime is a quilt sewn from entanglement, and invites us to look for its stitches in the statistics. None has won. All have scars. And the sky keeps adding data to the debate. In the next chapter, we'll leave principles and hack at limits, how close current instruments can really cut, what upgrades buy us, and why the next tiny improvement in timing or baseline could turn a philosophical fight into a measurable fact. If the horizon is a whisper, our job is to build microphones big enough and quiet enough to hear it. In this chapter, we get practical. What can our instruments truly resolve today? Where do they break? And what, exactly, do the next upgrades buy us? The size of the problem. For Sagittarius A, the ring we want to measure spans only tens of micro arcseconds, an angle so small that if a donut on the moon had a sugar grain missing, you'd need an Earth-sized eye to notice. That's why the Event Horizon Telescope works. It stitches radio dishes across the planet into a single virtual mirror. But building a planet-sized eye doesn't end the story. It starts the list of limits. Limit 1. Resolution versus reality. Angular resolution scales with observing wavelength and the maximum separation between dishes. We'd love to go to shorter wavelengths, higher frequencies, to sharpen the image. But the atmosphere turns fickle, coherence times shrink, and weather bites. On top of that, the galactic center sits behind interstellar plasma that scatters radio waves, like looking through frosted glass. Higher frequencies help, but demand pristine skies and ruthless calibration. What the next jump buys, adding more stations, especially in longitude gaps, fills in the of plane, transforming smudged donuts into sharper, less ambiguous rings. Pushing to higher frequencies carves through scattering and makes the photon ring substructure less hopeless to tease out. Longer, better distributed baselines push dynamic reconstructions past suggestive toward compelling. Limit 2. Time fights us. Scrar A is small and lively. The emission pattern changes on minutes timescales, the same timescale it takes to synthesize a snapshot with Earth's rotation. That breaks the usual trick of pretending the target is static while you fill Fourier space. Result: you're trying to assemble a puzzle whose picture keeps morphing. What the next jump buys: faster recording, better timing, and algorithms that do dynamic imaging, reconstructing a movie, not a still. Turn variability from a headache into a signal. Coordinated multi-wavelength campaigns match each radio wiggle to near-infrared and X-ray flares, tying light curve beats to structure on the ring. Limit 3. Polarization truth. Polarization maps the magnetic field, but it's delicate. Instrumental leakage, atmospheric antics, and calibration ghosts can fake lines where none exist. What the next jump buys: cross-checks between many baselines and strict polarization calibration harden the field line picture. Higher cadence polarimetry lets us watch the angle rotate during hotspot orbits and compare to models of magnetized turbulence near the innermost stable circular orbit. Limit 4. Phase is gold and fragile. Absolute phase is trashed by the atmosphere. We survive on closure quantities, closure phase, closure amplitude, that cancel common errors. They're robust, but information limited. What the next jump buys: more triangles and quadrangles of stations explode the number of independent closures, tightening constraints on ring diameter, brightness asymmetry, and potential photon subrings. Water vapor radiometers and better sight metrology stretch coherence time, rescuing more phase. Limit 5. The reconstruction temptation. Machine learning can paint breathtaking pictures from sparse data and hallucinate with equal talent. If you ask an algorithm for a donut, it might bring you a perfect pastry every time, whether the sky baked one or not. What the next jump buys: method pluralism, different imaging pipelines, different priors, blind tests on synthetic skies. When independent methods agree, confidence climbs. Publishing visibilities and closure data alongside images lets the community audit the picture, not just admire it. Beyond the ground, why space changes the game. Earth is big, but it's not enough. Put one or more radio dishes into orbit, and baselines grow beyond a planet's diameter. Suddenly, the razor-thin features predicted by strong gravity, the subrings that echo light looping once, twice, 3 times around the hole, move from poetic to possible. Space VLBI also lets you hover above the worst weather and choose baselines with surgical precision. The cost is fierce. Clock stability, data downlink, and formation flying at millimeter wavelengths are unforgiving. But the payoff is the most literal kind of clarity, the horizon's edgework in focus. A different frontier, faster eyes. On the ground, we'll also win by going quicker instead of just bigger. Millisecond-level timing of visibilities, coupled with dynamic imaging, lets us follow the orbital beat of hot spots without smearing. Think of it as raising the frame rate so the dancer's steps don't blur. What sharper really gets us? Sharper pictures aren't just prettier. They cash out as physics, mass, and spin tighter. The ring size and brightness asymmetry constrain the black hole's mass and inclination. Time, resolved asymmetry, and polarization trends box in the spin. No hair tests, subtle deviations from the Kerr geometry, once astrophysical clutter is modeled, would flag new gravitational physics. Photon ring tests, detecting the predicted geometric series of subrings, would be a direct signature of strong lensing and a new lever on the space-time metric. Where flares earn their keep, minutes-long flares are not noise, they're clocks. Measure their periods, polarization rotations, and spectral hardening, softening, and you triangulate orbital radius, field geometry, and particle acceleration. Stack many events, and you hunt for quasi-periodic oscillations, preferred beats that whisper the black hole spin and the location of the ISCO. A candid checklist for the next 5 years. Add stations to the global array, especially where longitude gaps hurt coverage. Push routine, observing to higher frequencies when weather allows, to cut scattering and sharpen edges. Standardize dynamic imaging so variability is modeled, not averaged away. Treat polarization like a first-class citizen. Rigorous calibration, higher cadence, multiband cross-checks. Expand multi-wavelength coordination, radio, NIR, X-ray with precise shared clocks. Publish raw and reduced data so results are auditable and repeatable. Notice the pattern. None of these steps requires a miracle. They require patience, engineering, obstinacy, and communities that agree to compare notes. That's exactly how we turned "maybe there's a ring" into images of a shadow, and how we'll turn "maybe there are subrings" into a verdict. What this means for our bigger theme. Every technical limit we've met so far, resolution, timing, polarization, phase, has an analog in information science. Sharper baselines are better encodings. Faster cadence is better sampling. Polarization honesty is error budgeting. Closure phases are invariants that survive noise. When we say black holes might be masterclasses in information processing, the lab manual we're writing to study them already obeys the same logic: redundancy, cross-checks, codes. So the plan is simple, not easy. Build wider eyes and faster clocks. Treat variability as a teacher, not a nuisance. Let many methods argue, then keep only what survives the fight. Keep and I and R comes S and. On a quiet night, when the galactic center flickers, point every instrument you can at the heartbeat and listen with discipline. The horizon won't speak louder for us. But with the right microphones, it won't have to. Imagine tearing a photograph into 1,000 pieces and throwing them into a storm. Hours later, somehow, you reassemble the picture perfectly. That, in spirit, is what error correction does. It fights noise with structure. And if our hunch about black holes is right, the universe uses a version of this trick at the brink of the event horizon. Start small. In everyday computers, a single flipped bit can crash a program. To prevent that, engineers store information with redundancy, extra bits that don't carry the message itself, but carry relationships that let you detect and fix mistakes. In quantum devices, the challenge is harsher. Qubits are fragile, noise is everywhere, and measurements can destroy the very state you're trying to protect. So the fix gets smarter. Instead of copying a qubit, which quantum rules forbid, you spread its state across many physical qubits in a way that hides the message in correlations. No single qubit knows the secret. The group does. Now scale that logic up, way up, to a black hole. Near the horizon, turbulence, magnetism, and gravity form a blender that scrambles patterns at lightning speed. From the outside, it looks like chaos. From the inside-out description, the one where spacetime itself emerges from entanglement, at scrambling isn't destruction, it's encoding. The information about what fell in isn't kept in one place. It's distributed across many degrees of freedom, woven into relationships that are hard to disturb and harder to read without the right key. Here's a clean way to hear it in your head. Think of 3 layers. The message, whatever falls in, atoms, fields, quantum states, stories. The encoder, the near-horizon dynamics that mix and spread that message. The archive, the collective state just outside the horizon, the glow, the fields, the long-term radiation bath, where the message hides as structure, not as a sentence. If the encoder is good, fast, redundant, and global, then small pokes from the outside can't ruin the archive. That's exactly what we need if information is to survive the worst environment nature built. So what does fast and global mean here? Fast means the mixing time. The time it takes for a localized pattern to be smeared across the whole system is short compared to the system's other clocks. Global means the pattern isn't trapped in one corner. It gets distributed so widely that you can kick any single part and the whole still remembers what it was. In quantum labs, we call such dynamics scrambling. In our black hole story, scrambling is the first stanza of the error correction poem. But error correction isn't just scrambling. It also needs checks, built-in relationships that let a decoder distinguish signal from noise. In code language, those checks are stabilizers, tests you can run without revealing the message. Tests that tell you what went wrong so you can fix it. At a horizon, the tests aren't experiments we can perform. They're constraints baked into the physics, conservation laws, symmetries, and the tight algebra that ties geometry to entanglement. If those constraints map to stabilizers in the emergent description, the edge behaves like a living code. Why does this matter for life outside the lab? Because the same three ingredients, redundancy, scrambling, and checks, are what our world now needs at scale. In communication, redundancy and smart mixing protect messages against eavesdroppers and noise. If a black hole teaches anything, it's that structure beats chaos. You can hide a message in plain sight by making the wrong view look like randomness. In computation, fault-tolerant schemes borrow the idea that no single physical part should hold the whole truth. You distribute the truth, test the health of the distribution, and heal it constantly. In storage, the lesson is brutal but beautiful. If you rely on one place, you lose. If you rely on relationships, you win. Data dies on lonely islands. It survives in archipelagos. Let's bring the metaphor back to the ring we can actually see. The bright crescent is not a monologue, it's a choir. Its brightness, polarization, and timing are linked. When the near side flares, the polarization angle can swing. When a hotspot orbits, the brightness climbs and falls in a pattern you can predict from geometry and speed. These link changes are the signatures of an engine that respects deep rules. They're not stabilizers in the code theory sense, but they rhyme with the idea, relationships carry truth. A quick caution. It's tempting to declare, the black hole is a computer. That's poetic and dangerous. Better to say, black holes obey design principles that computers aspire to. They protect information against catastrophic environments by refusing to keep it local and by weaving it into patterns that survive coarse pokes. If we imitate those principles carefully, we get systems that fail gracefully and heal quickly. How would we translate that into human-scale blueprints? Blueprint 1. Spread before you send. Before a valuable message crosses a hostile channel, mix it into multiple streams whose individual pieces look useless. Only the right recombination restores meaning. This is not just encryption, it's structure. First, communication, resilience by design. Blueprint 2. Health checks that don't spill secrets. Build diagnostics that reveal whether your system is okay without revealing what it holds. In quantum codes, that's stabilizer checks. In networks, it's integrity tests that flag corruption without exposing the payload. Blueprint 3. Embrace graceful degradation. If a black hole's archive loses a piece, the rest still knows what to be. Aim for systems where losing a node, a drive, even a data center is a bruise, not a stroke. That's not a backup plan, that's an architectural choice. Blueprint 4. Let noise do work. The horizon teaches a counterintuitive trick. When you can't fight noise, shape it. Scrambling turns targeted attacks into generic errors that codes can correct. In practice, we design protocols that randomize failure modes, converting sharp spears into dull rain. Listen to the emotional beat under all this. The darkest places in the universe might be teaching us that forgetting is harder than it looks. The cosmos doesn't delete, it transforms, and transformation is friendlier than disappearance. That idea changes how we think about memory, human, digital, and cosmic. It nudges us to build systems that transform under stress without losing themselves. A final image for the narration while the visuals stay simple. A sheet of translucent fabric stretched over a ring of light. Press a finger into the sheet. Your message. In a heartbeat, ripples run, and the dent disappears locally. But if you look closely, the fabric's weave has shifted ever so slightly everywhere. No single thread has the message. The weave does. That's the horizon's lesson. That's error correction, spoken in geometry. We're not done. A code without a decoder is a poem we can't read. In the next chapter, we'll follow the hardest path of all, what a decoder would even mean in a universe that honors causality, and how close laboratory systems, quantum simulators, analog gravity setups, and ultra-cold matter can get to rehearsing black hole logic without leaving Earth. If information can survive a black hole, what would it even mean to decode it honestly without breaking causality or inventing magic channels? A decoder, in our story, isn't a sci-fi box that pulls voices from the void. It's a method, a disciplined way to extract structure from long, faint, gravity-twisted signals so that what looks like noise begins to tell the truth. First, the rules we can't bend. No faster than light messages. Once something crosses the horizon, classical communication stops. Outside, only evidence. Everything we claim must be recoverable from what the universe actually gives us. Light curves, spectra, polarization, interferometric visibilities, maybe gravitational waves, nothing from inside. Computational honesty. If the decoder would take longer than the age of the universe to run, it's not a decoder, it's a wish. So what remains? More than you'd think. A decoder is a map from patterns to causes. Imagine we sit with years of multi-band observations, radio, movies, near the ring, near-infrared flares, occasional X-ray bursts, perhaps future gravitational murmurs from orbiting clumps. A decoder in this setting is a map that turns the statistics of these signals into statements about the geometry and dynamics near the edge, spin, and inclination, magnetic topology, turbulence scale, mixing speed, the presence or absence of any exotic near-horizon layer, not a single frame, but a lifetime of frames, woven together. How do we build such a map without hallucinating? 3 steps. Forward, honesty. Start with physics you can write down. Relativistic plasma, ray tracing, polarized transport, time variability. Generate synthetic skies across a wide range of parameters and behaviors. Invariant features. Instead of training on pretty pictures, extract features that survive noise, closure phases, polarization angle swings, crossband time lags, quasi-periodic beats, power spectrum knees. Cross-validation. A decoder that works must predict new nights from old nights, new bands from old bands. If it can't generalize, it doesn't know the language. It's just copying handwriting. This isn't an image enhancer. It's a translator between data and dynamics, built to be suspicious of itself. In practice, it looks like an ensemble of models that agree on the invariants and disagree loudly when the data asks for physics they don't contain. The disagreement is as valuable as the fit. It tells you where your imagination ran ahead of nature, why decoding is hard, and why that's okay. At a deep level, the full microstate of what fell in is scrambled into correlations that take eons to leak out. We won't reverse that tape. but we don't need the diary to learn the alphabet. If the near-horizon region encodes information with fast, redundant mixing, the statistics of the glow carry its fingerprints. In other words, we can't read the book, but we can learn the grammar. Think of it this way: if a storm speaks a language, you won't ask it for a sentence. You'll measure the syllables, dominant beats, preferred angles, repeatable phase relations, and from those, infer the rules that made the storm possible. Rehearsals on Earth, lab decoders. If the cosmos won't give us do-overs, we build analog stages where the same logic plays out under friendlier lights. Quantum simulators. Cold atoms, trapped ions, superconducting circuits, systems where we can engineer fast scrambling and measure how patterns spread. The key observable is a family of out-of-time order probes that quantify how a tiny poke grows into a global disturbance. We practice encoding a simple state, letting it scramble, then attempting recovery with limited, noisy measurements. The win isn't perfection. It's learning which checks and redundancies make recovery robust. Analog horizons, fluid flows, optical media, and bows. Einstein condensates can host effective horizons for waves. They're not black holes, but they let us test how boundaries shape noise and correlations. Do horizon-like regions force fluctuations into predictable patterns? Can we identify universal ratios between timescales and spectra that match the grammar we think the real horizon uses? These rehearsals don't decode Sagittarius A. They debug the idea of decoding what features matter, which summaries are honest, where models hide their biases. A prototype decoder, the 3-pane window. Picture the control room with a quiet, 3-pane display. Pane 1, time. A stack of light curves across bands, aligned by absolute clock. Software extracts candidate beats, orbit-like periods, lags, which band leads, and sudden phase flips in polarization. Pane 2, space. Interferometric closures distilled into a small set of geometric constraints: ring diameter, brightness, asymmetry, the strength of any ultra-thin features. No images, just the invariants. Pane 3, texture, power spectra, and higher-order statistics. How red the noise is, where the slope breaks, whether there's hidden coherence at unlikely speeds. The decoder's job is to find a single, evolving story that walks through all 3 panes without lying. If you need different physics to explain each pane, you don't have a decoder, you have excuses. When one set of assumptions fits time but fails space, or fits texture but fails time, the tool says, change the story. When a consistent story survives across nights and bands, that's a measurement. A caution about cleverness. Machine learning can help. Feature extraction, surrogate models, rapid parameter scans, but the point is not to crown a neural network king. The point is to ensure the decoder respects causality, unitarity, friendly accounting, and the known limits of the instruments. A convincing decoder publishes which features carried the conclusion and how sensitive they were to calibration, weather, and priors. Mystery is the enemy here. Interpretability is the ethic. What would count as a decoder win? 3 concrete victories we can aim for in this decade: spin and inclination from variability alone. Derive them consistently from the joint rhythm of brightness and polarization, without relying on static images, and see those values agree with ring size fits. Magnetic topology from angle choreography. Use repeated polarization swings during flares to distinguish between tangled turbulence and organized horizon threading fields. Repeat across seasons. Thin, feature bounds from closure statistics. Even if ultra-thin subrings remain invisible, place tight limits on their contribution by how they must perturb closure phases when present. Turn, perhaps, into upper bounds that future arrays can beat. Each win shrinks the space where exotic near-horizon stories can hide. Each win turns philosophy into parameter space. Why this matters beyond astronomy? You don't need a telescope to feel the spillover. The decoder recipe, forward honesty, invariant features, cross-validation, is the playbook for robust intelligence in the wild. It's how you build systems that explain their answers, survive noise, and fail loudly when the world asks a question outside their training. If black holes are master classes in protecting information, decoders are master classes in respecting it. So no, we won't pluck voices from beyond the horizon. But we can learn to hear structure where we used to hear static, and to read rules where we used to see blur. That's a decoder worth having, one that turns a universe of storms into a legible sky. In the next chapter, we'll widen the stage, bringing in gravitational waves, cosmic rays, and the possibility of multi-messenger echoes that let us cross-check the story of the edge with entirely different senses. Light is not our only messenger. The universe also speaks in ripples, particles, and whispers we barely know how to hear. If the edge of a black hole is the most stubborn editor of information, then multi-messenger astronomy is how we sneak around the margins, reading not one channel, but many at once. Start with the ripples, gravitational waves. When two black holes collide, space-time itself rings like a bell. The final tone, called the ringdown, isn't just loud, it's specific. Its frequencies and decays are set by the mass and spin of the remnant, and crucially, by the geometry of the horizon. In a perfectly no-drama world, those tones match a Kerr black hole with surgical precision. Listen carefully enough, and you get black hole spectroscopy, weighing and spinning the remnant, using nothing but the music of space-time. Some researchers have hunted for late-time echoes in that music, tiny, delayed repeats that could hint at exotic structure near the horizon. Most searches find nothing conclusive. A few reports suggestive patterns. Either way, the method matters. If the edge carries any extra texture, the ringdown is where the fabric should snag. One dataset won't settle it. Dozens will. The point for our story is simple. Gravitational waves give us a second sense that ignores dust, ignores darkness, and feels geometry directly. Our own central black hole, Sagittarius A, is too quiet to sing in the ground-based bands where heavy mergers ring, but the universe is generous. When a small compact object, like a stellar mass black hole, spirals into a supermassive one, the result is a slow, intricate duet called an extreme mass ratio inspiral. Its frequencies sit in the low-frequency range planned for space-based detectors. Those signals carry a map of space-time written over years of orbits, precessions, harmonics, tiny shifts that reveal the central mass, spin, and even subtle deviations from the ideal geometry. If we ever want to test no hair at the brink without a telescope, this is the way. Let a clock fall and listen to every beat. Now turn from ripples to particles. Near a black hole, magnetic fields twist like steel cables. Charged particles spiral along them, accelerating to extreme energies and radiating across the spectrum. In the near-infrared and X-rays, we see fast flares that track orbits close to the innermost stable circular path. In gamma rays, some black hole-powered systems throw tantrums bright enough to rattle detectors across the planet. And on rare occasions, a black hole's neighborhood may launch a neutrino, a ghostly particle that walks through light years of matter without a scratch. One neutrino, traced back to a flaring source, can link a high-energy engine to the same physics we see at longer wavelengths. Cosmic rays are the unrulier cousins, charged particles that bend on their way to us, but ensembles of them, combined with photons and neutrinos, still whisper about the accelerators that fire them. The lesson is the same. Light alone is a narrow story. Particles widen the plot. The power of multi-messenger work isn't any single detection, it's the timestamp. When fields at the brink twist, when a hotspot swings, when a shock forms in a jet, the sky doesn't speak in one voice, it choruses. A near-infrared brightening, a polarization swing, A radio lag, an X-ray hardening, maybe a neutrino, stacked in time, they form a sentence. With one channel, you get an adjective. With many, you get grammar. Here is a clean, honest example of the grammar we want. A rapid near-infrared flare rises and decays in tens of minutes. During the rise, the polarization angle rotates smoothly, an orbital signature. A radio brightening follows, delayed by cooling and expansion in the flow. The X-ray band shows a brief hard spike at peak, hinting at higher energy particles. Days later, the radio knot drifts outward in high-resolution images, as if launched by the event. No exotic physics required, just a choreography we can test. Get that pattern repeatedly, and you infer magnetic topology, orbital radius, and particle acceleration with fewer assumptions. If the pattern refuses to be tidy, if angles skip, lags reverse, or spikes arrive out of order, you learn that simple hotspot pictures are not enough. Either answer is progress. There's another messenger, quieter but ruthless: pulsars. A millisecond pulsar in a tight orbit around Sagittarius A would be a metronome in hell, ticking so regularly that every deviation becomes a measurement of spacetime. Radio scattering toward the galactic center makes such discoveries hard, but the payoff would be enormous. Mass and spin pinned with clockwork, frame dragging measured directly, perhaps even constraints on how the edge handles passing waves and fields. One pulsar could do for strong gravity what a lighthouse did for navigation. Where does this leave our secret scientist's theme? Multi-messenger data doesn't open a channel through the horizon. It does something subtler. It triangulates the rules that the horizon enforces. Gravitational waves test the global geometry. Photons and polarization test the local plasma and fields. Neutrinos and high-energy photons test the accelerators that the edge and its outflows power. If all three stories agree, information is conserved without drama we can see. If they disagree in repeatable, instrument-proof ways, then something in our rulebook, smooth horizon, simple geometry, ordinary vacuum, needs revision. For the voiceover, keep the rhythm simple. Light shows us the paint. Waves show us the wood. Particles show us the nails. If the frame is wrong, the whole house creaks in unison. What would a decisive multi-messenger moment sound like? Imagine a season when a long, patient, gravitational wave signal maps a supermassive black hole's spacetime to absurd precision. Simultaneously, horizon-scale radio movies catch repeated thin features that match those spacetime parameters. At the same epochs, polarization swings and crossband lags land on the same clock, pointing to a magnetic geometry that explains both. No single instrument claims victory. The agreement is the discovery. That's how we turn theories about information and horizons into measurements, not with one loud yes, but with many quiet consistencies. If this sounds like a far horizon, remember how quickly the last decade moved, from sketches of accretion disks to images of shadows, from speculative waves to catalogs of mergers. Each new sense we add shrinks the space where confusion can hide. And every time we fail to see something predicted, we tighten the leash on fantasy. Hold one picture as the visuals fade to a simple star field. 3 lines on a timeline: light, waves, particles, braiding around the same moments. No single strand reaches across the horizon. But together they outline the borders so crisply that we can't mistake what kind of wall it is. That's enough to change how we think about darkness, not as a place where truth dies, but as a place where truth demands more than one sense. If information is the real cargo of the universe, what carries it where geometry won't? One provocative answer is that entanglement itself stitches space-time together, that quantum links are not just invisible threads between particles, but the loom that weaves the cloth. In this view, the interior of a black hole and the world outside are not separated by a brick wall. They are 2 faces of a tapestry whose pattern is correlation. Start with a simple picture. Take two qubits in a maximally entangled state and separate them by a light year. Locally, each one looks like noise. Globally, the pair is more than the sum of its parts. Now, scale up. Imagine a vast many-body state, fields, excitations, modes, entangled so richly that no small region holds a clean, independent identity. The hypothesis says geometry emerges from these relationships. Where entanglement is dense and uniform, space feels smooth. Where it thins or tears, space pinches, rips, or stretches. Seen through that lens, a horizon is not just a border, it's a place where who is entangled with whom reorganizes in an extreme way. Outside observers can describe everything they see using degrees of freedom just outside the rim, the stretched horizon story. Infalling observers describe a smooth passage, no drama. Both stories can be simultaneously true if they're complementary encodings of a single underlying pattern of entanglement that neither witness can fully audit. The punchline is not that a tunnel opens, it's that the division between inside and outside may be a choice of description, policed by causality. Now add a bold flourish. If very special patterns of entanglement can behave like bridges in the emergent geometry, then the interior-exterior connection becomes less mystical. It doesn't let messages cheat light speed. It does something subtler. It guarantees consistency. The correlations needed to keep quantum accounting honest are the same correlations that, in the emergent picture, keep the interior from popping like a glitch. If the pattern is right, the horizon stays calm for the infaller while still letting the outside world remain unitary and causally sound. How do you narrate that without losing the room? Use pictures the ear can hold. Image 1. A fabric of tiny threads. When the threads cross and knot densely, the fabric tightens and smooths. When the weave loosens, holes form. Space isn't the cloth. The cloth is the entanglement. Image 2. Two distant patches of cloth, stitched by faint, orderly seams. They don't pull matter across. They align stories, a bookkeeping synchrony, not a tunnel. Image 3. At the horizon, the weave thickens. Patterns grow redundant. The fabric can take a hit without losing its shape, an error-correcting weave. Why should anyone outside theory care? Because this viewpoint turns our headline, "Secret Scientists Inside a Black Hole," into a statement about archives and redundancy. The scientists are the records of events, the microstate details of what fell in. The archive, if this picture is right, lives on the boundary in an encoded form that no single poke can destroy. The bridge metaphor says, the archive is coherent enough to support two valid stories, one for the outsider, one for the infaller, without contradiction. That's not a communication channel, that's consistency as a physical structure. Bring the idea down to an experiment you can actually imagine. Picture a controlled quantum device, hundreds or thousands of qubits, with a layout designed to mimic a holographic code. Prepare a state that, by construction, has an interior region whose information is redundantly present across many boundary qubits. Now start corrupting the boundary, erase a qubit, flip a few, introduce noise. A good code lets you reconstruct the interior data from many different boundary subsets. No single qubit knows the secret, the overlap does. This isn't a black hole, but it rhymes with the horizon's promise. No local disaster on the boundary is enough to erase the interior's truth. Where does the fearsome word firewall fit in this picture? It's the emergency brake that theory pulls if too many entanglement promises are made at once. If the outgoing radiation must be entangled with earlier radiation to keep information, and also be entangled with interior partners to keep a smooth horizon, something breaks, the math forbids. Double marriage. The bridge viewpoint says the way out is to redescribe the interior in terms of the same boundary degrees of freedom that encode the outgoing radiation. 1. Marriage. Two perspectives. Whether nature actually does this is not settled, but the narrative is crisp. Either there is drama at the rim, or the inside story is a boundary story wearing a different hat. Both options make concrete predictions about correlations near the edge. For the voiceover cadence, keep 3 sentences close. If space is woven from relationships, the horizon is a knot. If information survives, the knot is tight and redundant. If 2 stories agree without talking, the knot is doing the talking. A final grounded image for this chapter. Think of a sprawling library where every book is sharded across shelves, such that any 50 shelves let you reassemble any book. A fire breaks out in one aisle, another is flooded. The librarians don't panic, they raindex. The books were never living on a single shelf. The building can burn in places, yet memory does not die. That's the horizon's ambition. That's the bridge entanglement offers, not a passage for footsteps, but a guarantee that the catalog still balances when morning comes. We will never put a camera past the event horizon. But if entanglement truly shapes geometry, we don't need to. The rules that make an insight possible are readable at the rim, in timing, in polarization, in the self-similar fingerprints of lensing. Our job is to test those rules until only one story remains standing, the one whose knots don't slip when the sky pulls hard. Black holes are hot, not hot like a stove, hot like a temperature assigned by quantum fields to a place where classically no heat should live. That temperature is the headline of Hawking radiation, the faint glow by which a black hole very, very slowly leaks energy and, in principle, ages. If information is never destroyed, this glow is not just waste heat. It is a ledger, a long, patient accounting of what fell in. To feel the idea, think of the vacuum near the horizon as a restless sea of quantum pairs, appearing and annihilating everywhere, always. Usually, you can't harvest that jitter. Near a horizon, the geometry lets one partner fall while the other escapes, leaving behind a tiny deficit that the black hole pays by losing mass. The escaping particle, seen from far away, contributes to a thermal spectrum, a temperature inversely proportional to the black hole's mass. Big holes are cold, tiny ones blaze. This would be a cute footnote if not for unitarity, the rule that says quantum evolution preserves information. Pure thermal radiation is featureless, and it tells you nothing about the microstate that produced it. If a black hole simply evaporated thermally, information would disappear. The paradox is sharp. Gravity's most textbook object would break quantum theory's most sacred promise. 2 possibilities remain. Either the radiation is not perfectly thermal, it carries subtle correlations that, taken together, encode what fell in, or the horizon is not what we thought. There is drama that reconfigures the rules. The first route draws a page curve for the radiation's entropy, rising like thermal junk at first, then turning down as correlations pile up. The moment of turn is the page time, roughly when the black hole has radiated half its initial entropy. The second route invokes extreme fixes, like firewalls. Our narrative is agnostic. It demands tests. What can we test now? Not direct Hawking photons from supermassive holes. Those are colder than the cosmic background. But the logic of the ledger appears in accessible places. Thermal, looking noise with hidden structure. When we stare at the horizon's neighborhood in light, the statistics can look hot and random while still harboring long-range correlations. The outside world never sees the diary. It sees the grammar of how the diary is protected. Fast, scrambling. If the horizon region rapidly mixes patterns, then small, localized features disappear into a global blur on short timescales. That's a signature we can chase in variability and polarization. Conservation at work. Across many flares and seasons, totals balance, angular momentum traded the way magnetized flows predict, spectra hardening and softening in repeatable ways. The ledger doesn't shout, it hums. The time axis is the villain and the teacher. The evaporation time of a supermassive black hole dwarfs the age of the universe. the full ledger won't be read. But nature gives shortcuts in miniature, analog horizons where waves feel an effective point of no return. Quantum devices where scrambling and recovery can be staged in seconds. Ringdowns from colliding black holes whose quasi-normal modes let us do spectroscopy of the geometry itself. Each shortcut tests a piece of the ledger. Is the vacuum near a boundary really so rigid? Do correlations survive noise when only the right combinations are examined? Does geometry respond exactly as a clean horizon demands? Bring the ear back to human rhythm with 3 anchors. Heat is not random by default. Temperature describes averages, not the fine print. You can have a hot bath of photons whose collective statistics hide a message you cannot read without the key. Time is a filter. Early emissions look forgetful. Late emissions remember. The page curve is a promise about when memory shows up, not a license for signals to outrun light. Patience is power. Long monitoring reveals rules no single night can show. The ledger emerges as a trend that refuses to die when instruments and seasons change. An image for the voice, a ledger book with most lines blacked out, page after page. At first, it's useless. Then, as the pages fill, the blacked-out blocks begin to form patterns, repeats, symmetries, balances. You still can't read the sentences, but you can prove the accountant is honest. That is what the horizon owes us, if information survives. Not a confession, but a consistency so strong that deletion becomes the only unbelievable option. Does this change life? Yes, in the way discipline changes life. If the universe keeps a ledger even at its wildest edge, then the right way to build technologies is to keep ledgers faithfully too. Track entropy, respect reversibility where you can. Design for recoverability rather than perfect control. In practice, that means energy-efficient computation, because erasing costs heat, communication schemes that structure randomness, storage that plans for ages, not weeks. The cosmos is patient, our machines can be, too. Hawking's temperature started as an audacious calculation. Today, it is a principle radiating far beyond black holes, that places which seem to forget are often reclassifying. The event horizon remains a one-way border. The ledger remains slow and subtle. But if the sky teaches anything, it's that truth is stubborn, so stubborn that even darkness must pay it back over time. A black hole bends more than light. It bends stories. To keep our narrative straight, physicists draw a special kind of map, a Penrose diagram, that squeezes eternity into a page without breaking causality. You don't need the math to read one. You need a legend and a steady eye. Here's the legend. A Penrose diagram preserves light cones, the 45 degrees diagonals that mark the fastest influence. Anything inside a cone can be reached without exceeding light speed. Anything outside cannot. The trick is a clever rescaling of distances and times so that infinities, the far future, the far past, the far away, fit on the same sheet. Causality stays true. Rulers lie. That's fine. For horizons, who can talk to whom is the only question that matters. Start with flat spacetime. Draw a diamond. Past at the bottom, future at the top. Left and right edges are elsewhere. Light rays are straight diagonals going up, left or up. Right. Now add gravity. For a non-collapsed star, light cones tip inward a little near the mass, but every world line that starts outside can, in principle, escape to the top of the page, future infinity. Collapse changes the grammar. When enough mass compacts, the light cones near the center tip so far inward that some region's future points inexorably to a point labeled singularity, the place where our equations confess ignorance. The border that separates futures that can still reach infinity from futures that hit the singularity is the event horizon. On the diagram, it's a 45 degrees line, a light-like border. Cross it, and your future light cone no longer intersects the outside world's future, Stories sever. Two clocks, two readers. On the diagram, an outside observer's world line stays above the horizon. Signals from the infaller asymptotically pile up near the border, never crossing in finite coordinate time. The infaller's world line slips through in finite proper time, then ends at the singularity. Both are true. The diagram shows why the disagreement is not a contradiction, but a frame effect. That's our Chapter 2 experiment in ink. Real black holes spin. Spinning geometry twists the diagram's interior, frame dragging whirls. Additional light-like surfaces appear. But the essential causal picture remains, a no-return region bounded by an event horizon, an exterior where observers can still meet, compare notes, argue about data, and a deep interior where notes are no longer deliverable outward. The diagram is merciless about communication and merciful about imagination. You can draw many interior possibilities, smooth, spiky, bridged, without falsifying the outside story. The outside test is always the same. No signal escapes. Now layer in evaporation. If a black hole emits radiation, it shrinks. On a Penrose diagram, the horizon can curve inward, the singularity can terminate. In an extreme cartoon, the hole forms, lives, then disappears, leaving behind ordinary spacetime. Where did the interior go? The diagram refuses to say. It is a map of causal structure, not a surveillance tape. If information survives, it must be accounted for in the outgoing radiation's global correlations, a statement about the entire page, not a point. That's why patience matters. You don't judge a ledger by a single line. Use the diagram to settle myths cleanly in the script. Myth 1. From far away, you see the infaller freeze at the horizon, so nobody ever falls in. Diagram says, the outside observer's slices of time never show a crossing. The infallers do. Causality allows both experiences because no later comparison is possible. Myth 2. Maybe there's a quick detour through a tunnel. Diagram says, a traversable tunnel would require curves that let a time-like path exit to the outside world. The horizon's light-like border forbids that unless the rules are changed dramatically. Myth 3. Hawking radiation means the horizon leaks signals. Diagram says, radiation originates in the outside region's quantum fields. Its existence doesn't draw a new arrow across the border. It changes the long-term shape of the border itself. A narrative-friendly exercise. Describe a day in the life of a photon skimming the photon sphere. On the diagram, its world line hugs the 45-degree slope near the horizon, loops in angle, then escapes to the outside future. That single path explains the ring we image, the time delays we measure, and the way brightness piles on the side where motion swings toward us. No fancy interior story is required. The diagram reminds us the shadow is an outer phenomenon with inner implications, not a photograph of the singularity. One last service the diagram performs. It marks what we can change and what we must accept. We can add detectors, widen baselines, sharpen cadence. We can tighten every outside constraint. We cannot alter the fact that beyond the horizon, our future and theirs part ways. The event horizon is not shyness, it's structure. Accepting that frees us to obsess over what the outside can truly tell, the mass, the spin, the fields, the mixing speeds, the ledger's honesty. Everything else is poetry until the sky nods. So keep the diamond in mind as the visuals fade. Diagonals for light, curved lines for lives, a slanted border where futures fork. It is the simplest, honest picture of a place where stories end without ending truth. And it is the reminder, every time we are tempted by easy drama, that the most powerful plot twist in physics is often the one a clean map refuses to draw. Time feels simple. It flows. Clocks tick. We remember the past and guess the future. But near a black hole's horizon, time is not a river, it's a web, stretched, tilted, and stitched to gravity, so tightly that the everyday arrow we trust begins to wobble. In this chapter, we'll give that wobble a human shape, how time, dilation, entropy, and memory braid together at the brink, and why the arrow still points forward even where light itself gives up. Start with the cleanest picture: two observers, two clocks. One stays far away in calm space. The other, an audacious traveler, dives toward the horizon of a supermassive black hole. From far away, the traveler's clock appears to slow. Her radio pings arrive farther apart, redder each time, until they fade into silence. From her own view, the seconds march normally. She crosses the horizon in finite proper time. Two truths, one universe, no contradiction, just relativity, doing what it promised. If time can disagree this much, what keeps causality safe? A simple rule: light cones. Every event has an allowed future. Those 45 degrees wedges we could draw on a Penrose map. As long as world lines stay inside those cones, cause and effect behave. The horizon doesn't scramble causality, it truncates contact. After the crossing, no signal reaches the outside. Stories diverge, not because time breaks, but because conversation does. Now bring in the arrow. In daily life, the arrow of time follows entropy. 2. The tendency for systems to move from orderly states to disorderly ones. Ice melts, cream diffuses. Memories form in one direction because the records of the past are written into the present's microscopic details. If you could run every particle backward perfectly, you'd unmix the cream. But reality is brutal. Small uncertainties explode. Heat leaks. Precision dies. The arrow is statistical, not mystical. At a horizon, entropy becomes a character with a name: black hole entropy. It scales with the area of the horizon, not the volume inside. That's a hint as loud as a siren. The bookkeeping for everything a black hole swallows is written on the edge. When matter falls in, the horizon's area, its entropy, grows. The arrow points inward and forward: more swallowed stuff, more area, more entropy. Hawking temperature makes the story richer, but not softer. Over absurd timescales, the hole radiates. Its area can shrink as energy leaks away. The ledger's arrow now includes a slow return, correlations seeding the outside with faint structure. Forward, always forward, growth in, then a long, lawful unwinding out. Where do memories live in this drama? Not in a notebook inside the hole that someone can fetch. They live as correlations among the degrees of freedom that remain accessible to the outside: the glow, the fields, the late-time radiation. Think of memory as pattern. The universe preserves pattern best when it is distributed, not localized. That's why the horizon's area law matters. The edge is not a boundary you can peel like tape. It is a registry that refuses to be stored in one place. We can translate this into feelings a listener can hold. Feeling 1. Time near the horizon is elastic from the outside, ordinary from the inside. Elasticity is not chaos, it's geometry. Feeling 2. The arrow is written by records, and records are patterns. The horizon manages patterns by spreading them wide. Feeling 3. Forgetting is expensive. The easier it is to erase, the more heat you pay. The horizon, the hottest price list in physics, tells us erasure is not its business. Transformation is. This changes how we talk about life in the script. Life survives by recording DNA, synapses, disks. We keep what matters by copying, spreading, cross-checking. At the cosmic scale, the black hole seems to adopt the same ethic. Do not keep truth in a single place. Keep it in relations. The arrow then becomes the story of how relations change, how they thicken during collapse and thin during evaporation, how they scramble near the edge and slow drip back into the world as correlations we can. In principle, Here, the traveler's watch re-enters the frame. Why does her time feel normal? Because proper time, time measured along her own path, is the only time any of us truly experience. The outside observer's clock is a coordination tool, not a law etched on stone. For narration, lean into that intimacy. Your time is the path you walk. Their time is the map they draw. Near a horizon, both stay honest and stop comparing notes. A small parable for the visuals showed two identical metronomes. One ticks on a desk far from gravity's extremes. The other rides a rail toward the ring of light. On split screen, we keep their audio. At first, the beats match, then a tiny drift, then a heavy lag. The traveler's metronome never misses on her side. The edit for her track stays clean, steady. But the outside audio stretches, then thins, then dissolves into a low, fading throb. The audience hears dilation as music. Now the pragmatic piece. If the arrow is married to records, then monitoring is power. Long, disciplined observations turn the sky's flicker into memory we can analyze. That's why the story keeps returning to time series, light curves, polarization angles, lags across bands, ring-down tones. Each adds a line to the ledger. Each reduces the room where fantasy can hide. The arrow, for us, is the direction in which uncertainty shrinks when data accumulates, a final nuance. People ask, if time slows near the horizon, could we watch the whole future of the universe play out for the infaller? The answer, told gently, no. What the outside sees as slowing is a red-shifting, dimming, and information bottleneck, not a gift of extra scenes for the traveler. And the traveler cannot look out and see tomorrow's headlines. Her light cones remain local. Horizons are sensors, not theaters, so the arrow survives the edge. It points from fewer records to more, from local truths to distributed ones, from tidy patterns to scrambled encodings, and back again over eons. Time doesn't break at a horizon, contact does. What remains is a lesson shaped like a compass. Keep records, spread them. Respect the cost of erasure. Trust the direction that makes patterns easier to find, not harder. That is how the universe keeps going in one direction, even in the one place where everything else turns around.